Next thing that we're going to do is we're going to look at Bronsted-Lowry acidity from a qualitative perspective. We've looked at it from a quantitative perspective, namely we looked at pKa values and we talked about table 3.1 and how you should memorize that table. However, it says here to determine the relative strengths of two acids without knowing their pKa values, what do? We look at the stability of their conjugate bases and we compare their relative stabilities. Again, so let's say you have HA and it loses a proton to give you H plus and A minus. And then you have HB, another acid that loses a proton to give you H plus and B minus. What you do is you compare A minus and B minus. You look at the relative stabilities of these conjugate bases. And we know that the more stable the conjugate base is, the stronger the acid will be. Again, the stronger an acid is, the more stable its conjugate base will be. So what we do is it says to determine the stability of the conjugate base, what we're actually doing is looking at the stability of the lone pair on the conjugate base. So we're going to look really hard at the lone pair on the conjugate base and determine, well, how stable is this lone pair on this conjugate base? The more effectively that a conjugate base can stabilize that negative charge or the lone pair, the stronger the acid it will have come from. And there are four main factors that affect the stability of a negative charge. Number one, the type of atom that carries the charge. Next is resonance, which is something we covered in chapter 2. Then induction, and then the type of orbital where the charge resides. If you put those four factors together, they give you this handy little acronym called ARIO. And you are going to use ARIO on quiz 3. I'll ask you questions where you're going to actually just have pKa values memorized, but it might give you something where you won't be able to memorize the pKa, or it's something that we didn't look at. And so you can use ARIO to determine which is the stronger acid and and the way you do that is by looking at the more stable conjugate base. So let's start with atom A from ARIO. The type of atom that carries the charge, it says here, we can determine whether an oxygen or a carbon will better stabilize a charge. Let's just start at the second bullet point here. Here you have a negative charge on a carbon atom, right? We know that there's a carbon atom here. This is a bond line structure. There's a carbon atom, and there's also two hydrogens that aren't shown, but we know they're there, and we have our negative charge on a carbon. Whereas over here, we have a negative charge on an oxygen. Well, if you think about the second period of the periodic table, starting at the P block, you have boron, carbon, nitrogen, oxygen, fluorine. And so carbon and oxygen are in the same period. And when you have two atoms that are in the same period, the negative charge is going to be more stable on the more electronegative atom. That is what's going to better stabilize the negative charge. And therefore, we know that oxygen is going to better stabilize the charge than carbon. Therefore, since this is the more stable base, it must have come from a stronger acid. And if you compare the relative pKa of an alcohol versus an alkane, well, we know that the pKa of an alcohol was somewhere around 16 to 18, whereas the pKa of an alkane was somewhere around 50. So this, again, we know it comes from a stronger acid, and because this is a more stable base. However, what would you do if you had a negative charge on two atoms that are not in the same period, but rather in the same group? Let's say you were comparing water, H2O, and H2S. What would you do? Oops, not H2O and H2O, but H2O and H2S. What would you do then? Well, in that case, you look at the negative charge. Since the atoms are not in the same period, but both of these atoms are in the same group, the factor that's going to be most important is going to be the size of the atom. Can anybody tell me what's a larger atom, oxygen or sulfur? Not a trick question. What's a larger atom? Yeah, sulfur. Definitely sulfur, right? Because it's lower in the group. So let's go back to it. We've got water, H2O, and we've got hydrogen sulfide, H2S. Which one is a stronger acid? Well, let's look at their conjugate bases. If this loses H plus, you end up with OH minus, a hydroxide ion. And if this loses H plus, you end up with SH minus, it's called the hydrosulfide ion. And since oxygen and sulfur are in the same group, but we know that sulfur is larger, the larger atom is going to more effectively stabilize the negative charge. And since it stabilizes it more effectively, that means that this is going to be the more stable base. Ergo, it's going to be the weaker base. So weaker base, therefore H2S is the stronger acid. And in fact, that is definitely true, because if you compare the pK of water and H2S, the pK of water we already saw today was 15.7, whereas the pK of H2S, which wasn't in the table, is 7.0. So it is much more acidic than water. So to summarize, when we're just looking at a negative charge on two different atoms, if they're in the same period, we base it off of electronegativity. And if they're in the same group, we base it off of size. Again, going back to this slide, if the two atoms are in the same group, the larger the atom, the more stable the negative charge. However, if they're in the same period, we go by electronegativity. All right, there we go. So that's the atom. Well, what if you have a negative charge that's on two atoms and they're identical? What if we compare a negative charge on two oxygens? Well, we can't use atom to compare the conjugate base stability, and therefore we must go to the next letter of our acronym, which is R, and that stands for resonance. Let's say we were comparing this conjugate base with this conjugate base. Well, again, we can't use A because the negative charge is on the oxygen here, and it's on an oxygen here. However, if you think about resonance, this anion has no resonance stabilization whatsoever. There's no resonance structure you can draw for this atom. Whereas if you look at this ion here, you can draw a second resonance structure, which is shown here. What do we know happens when electrons are delocalized? We know that if electrons are delocalized, it enhances their stability. And since this conjugate base is more stable based on resonance, that means it comes from a stronger acid. And we saw that acetic acid had a pKa that was around 4.75, we'll just put 5, whereas the pK of ethanol was about 16, so about 16. And you can clearly see that there's a difference of 11 orders of magnitude in terms of the relative acidity of the two. So to summarize, what have we covered? Atom. If the negative charge is on two different atoms, we can compare their size or their electronegativity, depending on whether they're in the same group or the same period. Now, if we have the negative charge on the same atom, we're going to look for resonance structures. If one has resonance structures and the other one doesn't, the one with the most resonance structures is going to be the most stabilized. Therefore, it comes from the stronger acid. Well, what if you can't use atom or resonance? For example, what if you wanted to compare this carboxylic acid with this carboxylic acid? You can't use atom because the proton is on an oxygen atom in both cases. You can't use resonance because you could draw two resonance structures for both of the conjugate bases of acetic acid and trichloroacetic acid. So what do we use? We use induction. Let's draw the conjugate bases of both of these acids. The conjugate base of acetic acid looks like this, where we have the negative charge here. And the conjugate base of trichloroacetic acid looks like this, where we have the negative charge over here, like this. So we have 1, 2, 3 chlorines. Well, what's the difference between these two molecules? If you look at acetic acid, it just has 1, 2, 3 hydrogen atoms on this carbon that I have highlighted in black, whereas over here it's got 3 chlorines. What happens is that the electrons are withdrawn through induction or via induction from these chlorines, since chlorine is more electronegative than a hydrogen or a carbon. So it pulls electron density away from the oxygen, and it stabilizes that negative charge even more. Again, we can't use atom, we can't use resonance, but because chlorine is electron withdrawing, it serves to further stabilize this negative charge, which means that trichloroacetic acid is going to be a more stable, produce a more stable conjugate base, and therefore it is a stronger acid. Give me a thumbs up if you follow me on the concept of induction. Induction, and stop me if you have a question. You know, the crux of what I'm trying to explain is shown in this little paragraph here. It says electron withdrawing groups or atoms inductively withdraw electron density from their surroundings, and what do? They stabilize the negative charge. Again, the more stable it is, the stronger the acid it will have come from. Check out this here. This is in the same vein. It says explain the following trend. As you go from acetic acid, which is this molecule here, which has 1, 2, 3 hydrogen atoms on this carbon, and this would be chloroacetic acid, where you've got only 2 hydrogens and 1 chlorine. Then here you've only got 1 hydrogens, and then you got trichloroacetic acid. Look what happens to the pKa's. They drop. They get lower and lower and lower. Right? We see that this is the strongest acid, and this is the weakest acid. Could anybody unmute their mic and explain to everybody why the acidity increases as we add more and more chlorines?
Would it just be because the more chlorines there are, the more like cold it would be?
Sorry, could you repeat that? It kind of cut out.
Oh, sorry. Would it just be because like the more chlorines there are, the more like pull there is? I don't know how to
Absolutely. That's a perfect way of explaining it. Excellent. I completely understand what you're saying. Look, if you draw the conjugate base of all of these, and I'll just do it kind of quickly here. If you draw the conjugate base, okay, what my student is saying, who was that? Sorry, I can't tell who's speaking.
That was Tracy.
Hey, Tracy. What Tracy is saying is 100% correct. That's just as good as an explanation as I could provide. She's saying, well, it's pulling electron density away. You have the negative charge on an oxygen, so we can't use atom. You can draw 2 resonance structures for all of these conjugate bases. But what she says is, as you add chlorines, you've got more of that inductive effect, pulling more of that negative charge away, more and more and more. And the more chlorines you add, the more stable the conjugate base becomes. So we'll put here most stable, and then we could put down here least stable. I just a question just popped up here, and I actually have it written down in my notes. That's clever. But let's see here. I asked students a question one time. I said, what if you had this carboxylic acid where you had 3 fluorines instead of chlorines? Okay, so I'm going to put this in a blue box here. If you were to compare this acid versus this acid, so if I call this one A and I call this one B, could anybody tell me which one would be a stronger acid? Would it be A or B? Yeah, it's going to be A. Why would it be A? Because A has 3 fluorines, and fluorine is even more electronegative than chlorine. So its electron withdrawing effect is even stronger, even more pronounced. And if you look at the pK of this compound, this is called TFA, trifluoroacetic acid. It has a pKa that's equal to 0.23. Kind of cool, huh? There you go, higher electronegativity. Exactly, Angel, perfect. There we go. So we've covered atom, we've covered resonance, we've covered induction. Well, what have we got left? We've got orbital. And I'm sure you all remember hybrid orbitals from General Chemistry 1 and from Chapter 1 in this class. So what if we have a negative charge on an atom, 2 atoms that are identical, we can't use resonance, we can't use induction. Well, what can we do? We can look at the types of orbitals where the negative charge is residing. And what do we know? That as we go from an sp3 to an sp2 to an sp hybridized orbital, the orbitals get smaller and smaller because they gain more s character. And what happens as they get smaller and smaller, the electrons are closer to the nucleus. So the closer electrons are to the nucleus, the more stable they are. It also says the shorter the atomic orbital, the closer to the nucleus. And therefore, if you have a negative charge in an sp hybridized orbital, it's going to be more stable than if you have a negative charge in an sp3 hybrid orbital. Why? Just because that negative charge is going to be closer to the nucleus. So let's take a look at 3 protons. Let's take a look at this proton, and this proton. We see the relative pKa's of ethane, ethylene, acetylene. They're all just carbon-hydrogen bonds. Why do they have different pKa's? It's based off of the carbon atoms. This carbon is sp3 hybridized. This carbon is sp2 hybridized. And this carbon is sp hybridized. Let's draw the conjugate bases of each one of these. Just give me a second here. If I draw the conjugate base of this guy, it looks like this. If I draw the conjugate base of ethylene, it's going to look like this. And if I draw the conjugate base of acetylene, it's going to look like this. So you see we have a negative charge on a carbon, a negative charge on a carbon, and a negative charge on a carbon. If we bring out the acronym ARIO, we can't use atom because the negative charge is on a carbon for all 3 of these. You can't use resonance because there's no resonance structures to draw. You can't use induction because there's no electron withdrawing groups or atoms, and therefore we're left over with orbital. Again, what's the difference? Here, the negative charge is in an sp3 hybridized orbital. Here, it's in an sp2. And here, it's in an sp. Since an sp is smaller and it's a shorter bond, that means that these, we'll put here, electrons are closer to the nucleus. Therefore, they are more, or we'll put here, most stable compared to the other 2. Most stable. And this most stable conjugate base means it comes, or the more stable conjugate base is, it means it comes from a stronger acid. And we can see that acetylene is clearly a much stronger acid than ethylene or ethane. Give me a thumbs up if you follow me on the idea of orbital. Orbital. Cha? Okay, good. All right, so there we go. We've covered the concept of ARIO. And just something you might be wondering, could you Google ARIO and search it on YouTube? I'm actually not sure. I've never done it. Maybe you can. There's so many people out there on YouTube now. However, ARIO is a concept that comes from the Klein textbook. The Klein textbook. It's not some universally accepted, method of doing things that you would see in any other textbook. David Klein is the one who came up with this. As far as I know, I certainly didn't learn it when I was a student. All right. Well, let's take a look. It says, when assessing the acidity of protons, we generally use ARIO and as the order of importance of these stabilizing effects, so atom, resonance, induction, and orbital. It's typically helpful to use this order of priority when comparing the relative stability of conjugate bases. However, organic chemistry, my friends, is filled with exceptions. And it says here, not 100% reliable. Okay, there are exceptions. And if you're wondering, oh, sugar, does that mean, Mr. Dion, the entire quiz 3 is going to be one exception after another, just a whole quiz of exceptions? No. There's one exception that I want you to know. Okay, one exception that I want you to know, and that is when you're looking at an amine and an alkyne. Okay, so we'll put here amine versus alkyne. That's the only exception I asked you to memorize. So know this this exception. Okay, and if you want me to explain the exception, no problem, it's right here. Okay, it even says right here on the slide, ARIO sometimes fails. So we'll put a big wah wah. Okay, not always, but check this out. If you take acetylene, this molecule here that we just saw, and you react it with the conjugate base of ammonia, NH2 minus, what you produce is this carbanion with the negative charge on an sp hybridized carbon in ammonia. If you compare the relative acidity of your acid, okay, this is the acid, and this is the conjugate acid. If you compare their relative pKa's, you can see that ammonia is the weaker acid, and yes, the equilibrium is going to lie to the side of the weaker acid. I taught you that. However, if you had used ARIO, you would have got the wrong answer. Right? If you had looked at the negative charge on a nitrogen versus a carbon, you would have said, well, nitrogen, and I'll just scribble it up here. Nitrogen has an electronegativity of 3.0, whereas carbon has an electronegativity of 2.5. Therefore, the negative charge should be more stable on the nitrogen, and since this is the more stable base, the equilibrium is going to lie to the side of the more stable base. Yes, there we go. Okay, because the more stable base would come from the stronger acid, but that rationale wouldn't work. It doesn't work. It fails in this instance. All right. And so what's our conclusion? Conclusion is this. It says for some acids, there's no way around it. You just need to know the pKa values because there are exceptions to the ARIO priority rule. ARIO can get you out of a bind. I'm never going to ask you to apply ARIO when it won't work. However, I do expect you to know all the pKa's from table 3.1. And I expect you to know how to use that table. And if you think about it, anyone who's a organic chemist by trade, she or he will always have a whole host of pKa values memorized, and know piles of them and stuff. Did somebody have a question? Okay, somebody had their mic on. Anyhow, well, let's move on and let's take a look at a practice question. It says, and you can see how this would be a very easy question for me to put on a quiz. Predict which proton, red or blue, is more acidic in each of these compounds. So what do we got here? In A, we've got a red proton. We've got a blue proton. Could anybody just tell me, which one of these is more acidic? The red or the blue? Yeah, it's going to be the red one, right? Because if you go back to the table 3.1, back to table 3.1, we saw that a phenol, this hydrogen has a pKa that's around 10, whereas we saw that an aromatic compound, right, having just a proton like this, the pKa is around 43. And therefore, since this is a phenol proton, it's going to be much more acidic. Okay, we're talking about 10 to the 33 orders of magnitude. If somebody asks me, is there a YouTube video going over table 3.1? Yes, the lecture video that I just posted from earlier this morning where I went over it in class. All right, let's take a look at the next one. The next one, there's kind of a couple of ways. You know what, let's back up. Let's take another look at this one. Let's say you didn't know the pKa's, okay? You didn't know either of these pKa's. Could you use ARIO to solve this? Right? If you look at the proton in red and the proton in blue, the proton in red is on an oxygen, it's on an oxygen, and the proton in blue is on a carbon. Well, what's more electronegative, oxygen or carbon? Oxygen is more electronegative, and therefore the red proton would be the more acidic proton. So I'll put here more acidic. All right. Next one, we have a 1,3-dicarbonyl. We looked at the pKa's of both of these protons. I showed you that the pKa of a 1,3-dicarbonyl, its pKa was 9, whereas the pKa of a ketone, like acetone, was around 19. So if we hear pKa was around 19. So therefore, this is going to be most acidic. But could you use ARIO to solve this problem as well? Could you use ARIO to solve that problem? Could anybody answer how you would use ARIO to solve B? You might have to unmute your mic to do that.
My guess is it has to do with resonance once the hydrogen atom is lost off of that carbon.
Absolutely, absolutely. It's definitely to do with resonance. Yeah, so if we go and we draw that molecule out, just take a blank space here, a Taylor Swift blank space, and if you were to remove the proton in red, right, if you were to have, well, I'll just draw the carbon ion. So if you were to remove the proton in the middle, you end up with this, and you can draw a resonance structure like this, where you have the negative charge up on this oxygen, like that. But you can also draw another resonance structure where you put the negative charge up on this oxygen, like this. And so we have a total of 3 resonance structures that we can draw for this compound. So this is the red proton, whereas if we do the blue proton, so blue H+, if we were to just remove that one, then you end up with this carbon ion, and there's only one resonance structure that you could draw for that, where you would put the negative charge up here, like that, and so you have less resonance structures. And that's it. Again, if you have ARIO, you can't use atom, so you use resonance, and this one has more resonance structures. That means it's a more stable base, and it comes from a stronger acid. And so that's how you would use ARIO to solve that problem. Let's go back here. Where was I? Somewhere around here. And then the last one. So if we look at the last one, we've got a red proton and a blue proton. Anybody have an answer? Which one would be the most acidic, the red one or the blue one? Excuse me. Yeah, I think it's the, oh, I see nobody. Yeah, it's the red one, right? The red one is going to be more acidic. We use ARIO. The red one is on an oxygen, whereas this one is on a nitrogen. So this one is going to be more acidic. Could also do the pKa's. The pKa of a carboxylic acid was around 5, and the pKa of an amine was around 38. So either one of those is going to work to solve that problem. How are you going to master ARIO? You've got to keep practicing. Okay, you can watch videos. That's great. I think it's very handy to do that. However, the best way to master the content is to try practice problems. Well, let's go back to this whole predicting equilibria. Which side will the equilibrium lie to? And if we look at any kind of acid-base reaction, like this one here, where we have an acid and a base, and we have a conjugate acid, and we have a conjugate base, you've got 2 options to predict which side is the equilibrium going to lie to. Is it going to lie to the right, or is it going to lie to the left? The way that you can determine that is you can compare pKa values of the two acids, the acid and the conjugate acid, the equilibrium is going to lie to the side of the weaker acid. So we'll put here again, equilibrium lies to side of weaker acid. We'll put here higher pKa value. Or you can compare the relative stability of the two bases, so the relative stability of the two bases. And the way that you do that is by using ARIO. There you go. So you got two possibilities. So if you forgot a pKa value or you can't remember it, or it's something that I've never shown you the pKa value, then you would have to try to solve it using ARIO. So those are your two possibilities. Pretty cool, huh? And these are things that we use all the time as organic chemists. Let's take a look at question 3.27. It says predict the position of the equilibrium for the following reaction. Is it going to lie to the left or to the right? So we'll put here left or right. I'm going to give you 1 minute to take a look at this problem. If you think you know the answer, type it in the chat. And I'll give you, how long? 60 seconds to try to solve this problem. Hey, Siri, set a timer for 60 seconds.
1 minute. Counting down.
All right, 60 seconds is up. Anybody have an idea? Would the equilibrium lie to the left side or to the right side here? I think the equilibrium is going to lie to the right side in this case. Okay, yeah, it's going to lie to the right. Okay, well, let's take a look here. First thing we could do is we could use the pKa's. We know the pKa of ammonia. pKa is 38. If we have an sp3 hybridized carbon-hydrogen bond, the pKa is 50. And so since this is the weaker acid, the equilibrium is going to lie to the right-hand side. You could also use ARIO here. So if we use ARIO, we're going to have to use A, because here we have the negative charge on a carbon, and here it's on a nitrogen. Nitrogen is more electronegative, and therefore this is the more stable base. And this, so the more stable base is going to come from the stronger acid. So that means that this would be the stronger acid, and this would be the weaker acid. And so again, the equilibrium is going to lie to the side of the weaker acid. If you were saying, well, hold on, I thought you said when you had a negative charge on carbon and a nitrogen that it lied to the other side, that it lied to the side of the amine, of ammonia. No, I said that that was true. That exception was dealing with an alkyne, okay, when you have an sp hybridized carbon. But here, that's not what we're dealing with. We're dealing with an sp3 hybridized carbon, hydrogen bond, and therefore this would be the weaker acid. Okie doke. Okay. I'm going to skip this question here, and we're going to come back to this next class. Maybe I might change the question slightly. I haven't decided. Let's just skip that and let's move on to something called the leveling effect. And leveling effect is, something that's pretty important as a chemistry student. Let's say you have a bottle of sulfuric acid. You have, if we just draw a bottle and it says sulfuric acid on it, H2SO4, that's aqueous, of course, sulfuric acid. I mean, is there any sulfuric acid in there? Are there any H2SO4 molecules in there? Well, the answer is no, very few, because what's going to happen is sulfuric acid is a very strong acid, and thus when you put it in water, the equilibrium is going to lie hard to the side of hydronium and the conjugate base of the sulfuric acid. And thus, in the bottle of acid, we don't have any sulfuric acid. What we really have is H3O plus in there. And that's based off of something called the leveling effect. And so we need to know how to choose an appropriate solvent for an acid-base reaction. It says here the solvent should be able to surround the reactants and facilitate their collisions. However, it itself cannot participate in the reaction. Because water can behave as an acid or a base, we say it's amphoteric. It has a leveling effect on strong acids and bases. So summarized again, or basically rehashing what I already told you. In fact, I'll take this, select all of this, and I'll put it down here. There we go. It says here, acid stronger than H3O plus can't be used in water. Why? Because you end up protonating the water, you end up protonating the water and just forming more hydronium. And it says bases stronger than hydroxide cannot be used in water. Let me give you an example. A base that's stronger than hydroxide would be NH2 minus. So NH2 minus, you can't use that in water as a solvent, because if you put that in water, all it does is rip a proton off of the water. Sorry, shouldn't be aqueous. Anyhow, all it does is rip a proton off of the water to give you hydroxide plus ammonia. Again, if you have sulfuric acid in water, you don't have any sulfuric acid. You only have hydronium. And if you have NH2 minus in water, you don't have any of that. The only base you're going to have is hydroxide. Again, repeating myself, acid stronger than hydronium can't be used in water, and bases stronger than hydroxide can't be used in water. Well, it says here, an appropriate use for water as a solvent is when the base is not stronger than hydroxide. Let's take a look here. You have acetate ion. That's what this thing is called here. So let me just write it down because you'll see it from time to time. Whenever you see this, this is called acetate. So this is the acetate ion here. If you look at the equilibrium between the acetate ion and water, if acetate behaves as a base, attacks water, removes a proton, you end up producing this acid, which is a carboxylic acid. This is called acetic acid. It's the acid that's found in vinegar. And the hydroxide ion. Well, if you compare the relative pKa's, 15.7 and 4.75, equilibrium is going to lie to the side of the weaker acid. Therefore, water is going to be a good solvent for acetate, because the acetate is not strong enough to rip off many of the protons, if at all. You can get some reaction, but the equilibrium greatly favors the left side, and so water is an appropriate solvent in this particular case. We could actually put equilibrium arrows like this, where we have them mostly to this side and only a little bit to this side. Again, this is the same thing I'm showing you for the third time. Because water can act like an acid or a base, it has that leveling effect on strong acids or strong bases. Again, if you have sulfuric acid, this is H2SO4 right here, you put it in water, what it does is it transfers a proton, it's a proton donor, to water to give you hydronium. If you compare the relative pKa's of sulfuric acid and hydronium. Well, hydronium is significantly weaker, and therefore the equilibrium is going to lie to this side. And so an aqueous solution of a strong acid, like sulfuric acid or hydrochloric acid, can be viewed as nothing more than an aqueous solution of hydronium ions. The main difference is that between between concentrated and dilute sulfuric acid is the concentration of H3O plus or hydronium in that solution. All right, well, let's take a look here at something kind of interesting. Bases stronger than hydroxide cannot be used with water. We saw that already. For example, we wouldn't be able to perform this reaction in water. Let's take a look at this reaction. We have an alkyne. We know that this proton has a pKa of around 25. And here we have an amine, and amines have pKa's that are around 38. Right? This is my acid. This is my conjugate acid. Okay, well, the equilibrium or the arrow is correct. It's going to lie to the side of the weaker acid. Everything here is fine. However, what they're telling you is that you could not do this reaction in water. You might think, well, I used water for everything in general chemistry, which is true, but you could not use H2O as a solvent here. If you try to do that, it will not work. You will not get this reaction. Well, what the heck's going to happen? What's going to happen is that this base here is going to react with the water. Let me prove it to you. You're going to get a side reaction where this anion is going to react with the water. Look, you have the N minus ion. It's going to react with water. And it's going to rip a proton off of that water to form the amine plus hydroxide. Now let's compare the pKa's of the two acids. This is our acid. This is our conjugate acid. The pKa of water, pKa is equal to 15.7. The pKa of the conjugate acid, the amine, pKa is equal to 38. Well, this is by far the weaker acid. Therefore, the equilibrium is going to lie to this side. So what happens is when you put water in this, or if you tried to use water as your solvent, the water is just going to react with this, the conjugate base of the amine, and you end up producing the amine and hydroxide, and you would get none of this. And therefore, water would not be an appropriate choice of solvent. And you can see why being in organic chemistry is a high-paid position. You know, people who are organic chemists usually make good money. The reason why is because, let's say this reagent cost thousands of dollars, and you said, oh, I'll just use water as the solvent. Well, there you go, thousands of dollars down the drain. And thus, a good organic chemist, she or he will be able to choose the appropriate solvent for the reaction in order to maximize the quantity of the product. All right. Well, let's do two more sections, and then we'll take another break. And the next two sections are very short. In fact, one of them we already looked at. We were talking about solvating effects and pKa's, or maybe, I can't remember, maybe we looked at this or maybe we didn't. Either way, it's neither here nor there. Take a look at these two alcohols. This is a pretty cool example. You have terbutanol and ethanol, and there's a difference in pKa between these two of 10 to the power of 2, which again is 100. We saw that earlier today. But why is it that ethanol is so much more acidic than terbutanol? You can't use the A from ARIO, you can't use resonance, you can't use induction, and you can't use orbital. You got nothing. So how do you explain it? Well, the way that you explain it is by looking at, again, their conjugate bases. And how do these two molecules differ? The way that they differ is the R group. You can see that this R group over here is big, and this R group over here is small, and that actually plays a role in stabilizing the conjugate bases. Check this out. If we think about our conjugate bases, whether it's the terbutoxide or the ethoxide, the way that they're stabilized is by solvent molecules gathering around the negative charge on the oxygen. But when we have the ethoxide, we can squeeze more solvent molecules around it to provide more stabilization of that negative charge. Whereas with the tert-butoxide, since you've got those big groups, you can't put as many solvent molecules around it. And so the conclusion is that since the tert-butoxide is sterically hindered by all these CH3 groups around it here, it's not as stabilized by the solvent, and therefore it's not going to be as good at donating a proton. And that is why ethanol is a stronger acid than tert-butanol. The next section I want to look at is just one slide for it, section 3.8, just one stinking slide, which deals with counterions. You might remember from general chemistry, you would have talked about complete ionic equations and then net ionic equations. And net ionic equations were ones where you canceled out spectator ions. And spectator ions or counterions are ions that are required to balance the overall charge of a solution. However, we usually don't include them in a reaction because they're not participating in the reaction. It says here they do not, generally speaking, play a significant role in reactions, and so we just leave them out. Like, you just leave them out? Yeah, just leave them out. Just don't even write them in. And again, they're there, but as organic chemists, most of the time we leave them out because in chemistry 3101, they are very rarely of any significance. Take a look at this reaction here. We have NaNH2 plus water gives you ammonia plus sodium hydroxide. We can see that there's two metals here, right? You have a sodium here, a sodium here, and a sodium here, but those are just sodium cations, right? So if you write out everything in its ionic form, you would write out Na plus NH2 minus plus H2O produces ammonia plus Na plus hydroxide. Well, what didn't change on both sides? The only thing that never changed was the Na plus, and so that is our counter ion or our spectator ion, and we like to just leave it out. You can't just have a negative charge in solution. There has to be a positive charge balancing it out, but we just assume that there is a cation in solution. And again, most of the time, I just leave the counter ions out because they do not play a significant role. And there's very few exceptions in this class. You don't really have to stress about counter ions a whole lot. The next section that we're going to look at is Lewis acids and bases. But let's take a quick break before we do that.